Greetings of the day, dear students. In this video, we are going to discuss about the methods of improving the power factor or power factor improvement, right? Before going into the discussion of improvement of power factor, it is very important to understand what is the power factor, what is its definition, right? And how the power factor will be in a DC circuit, and what will be the power factor if the supply is AC in AC circuits. And also we should understand the impedances of resistive, inductive and capacitive elements, and we have to discuss about its need, its importance of improving the power factor. What will happen if the power factor is not improved? What are the consequences on the electrical system, right? And then we are going to discuss about the methods of improving the power factor using with the help of capacitor banks, synchronous condensers and phase advancers. How these three methods are going to help to improve the power factor. And finally we will discuss about how to calculate the power factor. What is the method we have to follow in order to calculate the power factor? All those things we are going to discuss in this video, right? Dear students, this topic is very important, okay? And before entering into the topic directly, some basics are very important. Some basics are very important. Dear students, if you are having a source which is supplying some voltage V, and you have connected a load, now depending upon its power rating, right, this load is going to draw some amount of current. This load is going to draw some amount of current. Now there will be some angle existing between the voltage and current depending upon the nature of the load. Depending on the nature of the load, right, there will be some angle existing between the voltage and current. Now the cosine of the angle between the voltage and current is called power factor. The cosine of the angle between the voltage and current is called the power factor. So how do you understand that? For example, if the load is resistive in nature, then if the applied voltage is V across the load and the current drawn is some I, if the applied voltage is V and the current drawn is I, if it is a resistive load, both voltage and current will be in phase. This is very important. The voltage and current will be in phase, and the angle between voltage and current is 0 degrees. Now if you are asked about the power factor, right, cos of phi, right, cos 0 degrees is 1, the power factor is unity. Similarly, if the load is purely inductive in nature, if you have applied some voltage V and the current drawn by the load is some I, now the angle will be, if it is a pure inductor, it will be 90 degrees. Right? But the current will be lagging the voltage. The current I lags the voltage. I will be lagging the voltage. I lags V by 90 degrees. If it is capacitive load, here also the angle difference will be 90 degrees, but current will be leading the voltage. If it is a capacitive load, I leads V by 90 degrees. So these are some of the basics, just to understand that if it is a resistive load, the angle will be 0. If it is inductive load, 90 degrees, and capacitive load also 90 degrees, but it depends. I lags the voltage if it is inductive load, I leads the voltage if it is capacitive load. This is what here it is shown. If this is the voltage waveform and this is the current waveform, right, and here the current is lagging the voltage by some angle phi, In this context, if this is the voltage and this is the current, in this figure current is leading the voltage by some angle phi, right? So these are the some of the basics. Now in terms of power also the power factor can be defined. We have defined now power factor in terms of voltage and current. Cosine of the angle between the voltage and current is called the power factor. Or in another manner we can express it in terms of power. Dear students, while expressing that in terms of power, it is important to understand the different variables of power or different names we are having. If it is active power or real power or true power, we will denote with letter capital P. This is very, very important. So the P is active power or real power or true power. We will express it in P, and the formula is VI cos phi. Product of the voltage into current into cosine of the angle between the voltage and current. Cosine of the angle. This phi is the angle between the voltage and current. And the units are watts. Similarly, if it is reactive power, it is denoted with letter Q, and it is given by the formula VI sin phi. And the units are volt ampere reactive. VAR indicates the volt ampere reactive. This is also unit for power, but that is for reactive power. Now one more power we are having, that is the complex power or apparent power, or total power S, which is simply the product of voltage and current, and the units are volt amperes. So dear students, if you observe, for the powers, if it is P, we have expressed it in watts. If it is Q, we have expressed the power in volt ampere reactive, and if it is S, complex power, we have expressed it in volt amperes. If the magnitude is high, we will express this power in kilowatts. If this one, we will express it in kVAR, and this one we will express it in kVA. Right? Now with respect to the angle, with respect to the power factor, simply now VI cos phi divided by VI will give us the power factor cos phi. So dear students, it is simply the ratio of actual power to the apparent power. If you take, we will get the power factor. Two definitions we have covered with respect to the power factor. One is the cosine of the angle between voltage and current, or the ratio of actual power to the apparent power will give you the power factor cos phi. So this is the definition with respect to the power factor. Like this we have to understand, right? Now coming to the DC circuits, dear students, what happens is, if it is a DC circuit, for DC supply, the inductors and capacitors under steady state condition, right, they will behave like a short circuit and open circuits. So finally the nature of the circuit in DC supply or for DC circuits, it will be resistive in nature. Once it is resistive in nature, the angle between voltage and current, this angle phi will be equal to the 0 degrees. So the power factor, as we discussed earlier, power factor equals to cos phi equal to cos 0 degrees will be equal to 1. This is very, very important. If it is DC circuit, the inductors and capacitors will behave like a, if it is an inductor, it behaves like a short circuit, and if it is the capacitor, it behaves like a open circuit in its steady state. But whereas if it is an AC circuit, some angle will be existing between the voltage waveform, some angle will be existing between the voltage and current. If it is highly inductive in nature, current lags the voltage by phi. If it is inductive in nature, if it is capacitive in nature, current will be leading the voltage I. Current leads the voltage by some angle phi if it is capacitive in nature, right? So this is very, very important. Now dear students, electric power, we know that simply given by voltage across the element into current through the element, voltage across the element into the current through the element. The units are watts power and joules per second, right? Now dear students, if it is purely resistor, the impedance Z here indicates the impedance. Z is the impedance of the element, impedance which will be expressed in ohms. The units are ohms. If it is purely resistor, Z equal to R plus, there is no reactive component, plus J 0 ohms. If it is inductor, Z equal to 0, pure inductor, Z equal to 0 plus J XL ohms. Pure capacitor, Z equal to 0 minus J XC ohms, where XL indicates the, XL is called inductive reactance, and XC, X subscript C, is called the capacitive reactance. Now XL is given by 2 pi FL and XC is given by 1 by 2 pi FC, where F indicates the frequency of the supply. F indicates the frequency of supply. For Indian system, it will be 50 Hz, frequency of the supply, right? 50 Hz for Indian system, right? So now if you are having, if the load nature is if the load is having both resistive and inductive nature, then the impedance we can write it as Z equal to R plus J XL, right? It is in the form of some it is in the form of complex form. We have written for rectangular form, we have written it in rectangular form. Once it is in rectangular form, the angle theta is given by tan inverse of XL by R. So this much of angle will be there between the, if current flowing is I and if you have applied some voltage V, now this much will be the angle between the voltage and current. It depends upon the value of XL and R. XL is nothing but 2 pi FL. Now cosine of this angle will give you the power factor. Cosine of that angle will give you the power factor, right? In AC circuits, the impedance is important, whereas in DC circuits, this inductor and capacitors in steady state, they are behaving like a short circuit and open circuit conditions, elements behaving like a short circuit and open circuit elements. Now dear students, if you recollect, the total power, electric power S is given by VI, the units are volt amperes, and the active power is given by VI cos phi, the units are watt, and the reactive power QV is given by VI sin phi, volt ampere reactive. Mathematically, you can write it as S equal to P plus J Q. So if you want its magnitude, mod S will be equal to the root over P square plus Q square, P square plus Q square. If you want the angle phi, it is simply tan inverse of Q divided by pi. Once if you are given the active power and reactive power, you can easily calculate the angle phi. Once you know the angle phi, the power factor can be calculated using the power factor equals to cos phi, right? So from this you can obtain the power factor, but this basic is very, very important. S equals to P plus JQ. So mod S is given by root over P square plus Q square, and the angle phi is given by theta phi equals to tan inverse of Q by P. This is what we have expressed it in the form of a triangle. So on x-axis you have taken the real power expressed in kilowatt, and this is the real reactive power expressed in kVAR, and this is the apparent power S, mod S equal to, this is the S, this is P and Q. So S equals to root over P square plus Q square, or S square equals to, or in another manner you can write it as S square will be equal to P square plus Q square. S square equal to P square plus Q square. This is also important, dear students, right? So simply to say, if you want power factor 5, tan inverse of Q by P, you will get 5, and cosine of that 5 will give you the power factor. If you know the impedance, then also you can get the value 5. Simply tan inverse of XL by R if it is inductive load. If you are having capacitive load, for example Z equals to some R minus J XC is there, then also you can write phi equals to tan inverse of XC by theta. The angle theta will be tan inverse of XC by R. If you are having all three together, for example if you are having resistor, inductor and capacitor all together, then impedance all are in series, right? Z equal to R plus J bracket of XL minus XC. If you want angle theta phi, at that context tan inverse of XL minus XC divided by R. So all the possibilities are discussed. Whether it is resistive or inductive or capacitive, is a combination of RL or RC and RLC. In all the cases, it is important to find out the angle phi. Once you know the phi, the power factor cos phi is given by power factor PF equal to cos phi or cos theta. Now let me discuss about the importance of the power factor. Why it is that much important to improve the power factor, or what happens if the power factor is not improved? What happens if the power factor is not improved? Dear students, if you observe, if you are having a source, and if it is connected to the load, now the amount of current drawn by the load is inversely proportional to the power factor cos phi. Very, very important, dear students. The amount of current drawn by the load is inverse. If the power rating is P, right, the amount of current drawn by the load is inversely proportional to the power factor. So how do you understand that? If the power factor is very, very low, it is going to draw more current for the same given power rating and voltage. For the same power rating and applied voltage, if the power factor is low, it is going to draw more amount of current. Once it is drawing the more amount of current, already between the source and the load, because more amount of power will be wasted in the form of losses. For example, if the amount of current drawn is to be more, then the conductor size we have to select should be having large cross sectional area. So in order to transfer the same amount of power, but if it is done with the help of huge amount of current with low power factor, then the cross sectional area of the conductor should be more. Then it will overall increase the cost of the equipment. The cross sectional area of the conductor should be more in order to carry the more amount of current, to transfer the same amount of power but at low power factor. So this is the important point. Similarly, once the current is more, obviously we know that I square or amount of power will be wasted in the lines, and the power loss also will be more. Once there are losses, right, with respect to the efficiency, output power by input power, where the output power will be nothing but the input power minus power loss, right? Once the losses are more, you will get less output and the efficiency will be low. This is the another drawback. The efficiency of the system will get reduced, because With the low power factor, it is drawing the more amount of current. If the current drawn is more for the same amount of power, the power loss will be more. The power loss is equal to I square R. If the power loss is more, the power output will be less, because the power output is nothing but the input power minus loss. If the losses are more, output power will be less. If the output power is less, efficiency will be less. These are the consequences. The overall efficiency of the system will be reduced. And another important point is, dear students, please observe this example carefully. For the same amount of power, for example, a load is there which requires some 100 kilowatt of power. A load is there, it requires 100 kilowatts of power. Now what should be the size of the transformer? The size of the transformer in kVA. What should be its size will depend upon the power factor of the load. How do you understand that? Already we have seen that kVA, S rating can be simply given by P divided by cos phi. P divided by cos phi. Now dear students, if P is 100 kilowatt, if the power factor is 1, then what will be the S? S will be 100 kVA transformer is enough. 100 kVA transformer is enough to serve 100 kilowatt load when if cos phi is equal to 1. Now if the power factor is only 0.8, if the power factor is 0.8, then the transformer size must be 100 divided by 0.8, which will be 125. 125 kVA of transformer is required. Now if the power factor is very low, if the power factor is only 0.5, now we require some 200 kVA size transformer. So if you observe, with the decrease in the power factor, the size of the transformer to serve the same load is more or bigger in size, So this is the major drawback. That is the reason why you have to maintain the power factor close or nearer to the unity. The kVA rating of the equipment will get increased with the decrease in the power factor. If the power factor is very low, the kVA size required will be more. So dear students, these are the major drawbacks. Current drawn will be more at low power factor. Power losses will be more at low power factor. Efficiency will be low at low power factor. Right? Output power will be low at low power factor, and the kVA rating of the equipment will be increased at low power factor. Because in order to overcome all these things, it is very important to maintain the power factor. Ideal case is unity. If the power factor cos phi is equals to 1, then this is the best one. But practically maintaining exactly 1 will be difficult. You can maintain up to some 0.99 or 0.98 or 0.95, like that we can bring it, and we will take care to maintain as much as close to 1. In order to make it improve the power factor, we can do it using the capacitor banks, synchronous condensers and phase advancers. Using the capacitor banks, synchronous condensers and phase advancers. How we can achieve that? For example, if you are having a load which is demanding some S equals to P plus JQ, the load power S, the amount of reactive power required can be provided locally with the help of a capacitor bank, which will be inserted in parallel to the load. If you insert a capacitor bank like this in parallel to the load, and this capacitor bank will inject the reactive power to the line, and whatever the amount of reactive power required, at least some part of the reactive power required by the load is generated as is injected by the capacitor bank. Once if you inject some amount of reactive power with the help of the capacitor bank, capacitor bank, then the angle difference between the voltage and current will be reduced. Once the angle difference is reduced, the power factor is improved. Like this we can achieve. One more thing, the most of the loads are inductive in nature. Along with active power, they also require the reactive power. They also require the reactive power. In this formula, S is the total power, P is the real power, and Q is the reactive power. Q is the reactive power, right? So, for example, without capacitor, if the angle between voltage and current is some phi1, by adding some capacitor, the angle difference between the voltage and current will be reduced. The voltage and the angle difference between voltage and current will be reduced, right? Next one is with the help of synchronous condensers, which is nothing but an overexcited synchronous motor. In parallel to the load, you will connect a synchronous motor, a three-phase synchronous motor, which will be operated under overexcited state. Under overexcited state, the synchronous motor will behave like a synchronous condenser. Almost it behaves like a capacitor, and it is going to inject the reactive power into the lines. It is going to inject the reactive power into the line, and it will take or consume the active power. This synchronous condenser will take the active power and it will inject the reactive power into the line, so that some amount of or some fraction of reactive power required by the load will be met or generated locally with the help of this synchronous condenser. And like this you can improve the power factor. But this three-phase synchronous motor should work under overexcited state. And the same motor can be operated either in the leading power factor or lagging power factor or unity power factor, depending upon the excitation provided to the synchronous motor. It can get operated in leading power factor mode, lagging, and unity power factor mode. Next one is with the help of phase advancers also we can improve the power factor. This is nothing but an AC exciter, mainly used to improve the power factors of the induction motors, right? They are mounted on the shaft of the motor and connected to the rotor circuit of the motor. They will be connected to the, if you will have a stator and you will have the rotor, right? And these things will be connected on the rotor shaft, and it improves the power factor by providing the exciting ampere turns that are required to produce the required flux at the given slip frequency, right? This ampere turns will increase the it can be made to operate at the leading power factor mode. Using this phase advancers also we can improve the power factor. So these are the three different methods: using the capacitor banks, synchronous condensers, and phase advancers. We can improve the power factor. Next one is how do you calculate the power factor? Already you are familiar. Power factor, this point should not be forget. Cosine of the angle between the voltage and current over R in terms of the ratio of P divided by S will give you the cos phi power factor P, because already P means VI cos phi. The formula for S is VI. If you take its ratio, you will get the power factor cos phi. So with for example, if you want to calculate the power factor, what we can do is, if this is the given source and this is the load, and if you are given a wattmeter will be having the four terminals. And it is going to have M indicates main side, L indicates load side or line, C is the common terminal, C for common, and V for potential. If you this is called current coil CC, and this is called potential coil PC. The current coil must be connected in series to the load, and the potential coil will be connected in parallel to the load. Like this the wattmeter is to be connected. Once the wattmeter connections are made, and also in order to measure the current drawn by the load with the help of ammeter, you will connect in series to the load. It will measure the current drawn by the load, and parallel to the load we will connect the voltmeter in order to measure the voltage applied to the load. So using these three meters, we can get the current drawn by the load, voltage applied to the load, and power drawn by the load. Now whatever the reading, for example, if the wattmeter has read some the reading of wattmeter is equals to the 1000 watts, if it is showing, its meaning is this value is equal to the VI cos phi. Now already with the help of voltmeter ammeter, you know the voltmeter reading. For example, if the voltmeter reading is some 220 volts, and if the ammeter reading is some 3 amperes, right? On substituting the values of voltmeter and ammeter reading, we will get the power factor cos phi. Here in this context, for example, the wattmeter reading is 1000 watts divided by voltmeter reading is 220 into, if the ammeter reading is some 3 amperes, we will get it as here if the current drawn is some 5 amperes, we will get it as 1000 by 220 into 5. So here 220 into 5, which is around 1100. So 1000 divided by 1100, which is around 1000 divided by 1100, we are getting it as 0.909. So therefore the power factor cos phi is equals to 0.909. Like that we can calculate the power factor depending upon the wattmeter reading and voltmeter and ammeter reading. But wattmeter always reads VI, gives you the VI cos phi value. Wattmeter always gives you the VI cos phi value, and with the help of voltmeter you will measure the voltage, and with the help of ammeter you will measure the current, and VI cos phi divided by VI will give us the power factor, right? So this is how we can measure the power factor. So these are all the important points, dear students. Simply to say at last once again, power factor is the cosine of the angle between the voltage and current, or it is the ratio of active power by apparent power. If the power factor is low, what happens? What are the consequences? The loads will draw more amount of current. If the current drawn is to be more, the conductors sizes, cross-sectional area size of the conductors will increase. And if the current drawn is more amount of power will be wasted. I square R amount of power will be wasted. If the power wastage is more, efficiency will be low. And to serve the same amount of load, if the power factor rating is low, the kVA rating of the equipment, the size of the equipment will be increased. These are the drawbacks. For improving the power factor, we are having capacitor banks, synchronous condensers, and phase advancers. Capacitor banks will be connected in parallel to the load, and it will inject some amount of reactive power required for the load. By doing so, it will reduce the angle between the voltage and current. Synchronous condensers, nothing but the three-phase synchronous motors which are operated under overexcited state. During that state, they are going to supply the reactive power. It draws some active power and injects the reactive power to the system. Next one is the phase advancers. While calculating the power factor, wattmeter always reads VI cos phi value, right? And with the help of voltmeter and ammeter, we will measure the voltage and current. Taking its ratios, we will get the power factor. Once you know the angle phi, you can also calculate the reactive power. Already you know the voltmeter reading, ammeter reading into sin phi will give you the reactive power also. But wattmeter always reads active power. If you want to measure the reactive power, you can simply, once you know the phi value, you can also measure the reactive power drawn by the load. Right? Thank you.